session of the first day. I just have a very quick announcement about masks. So for those of you who are COVID phobic like I am, or would like to try upgrading your mask, we have a supply of N95 respirators at the registration area. And just if you grab one, don't toss it away immediately. It actually lasts for quite a while. You can sort of reuse it for a couple of days. I guess that's all I have to say. Thank you.
Good morning, everybody. My name is Rainer Blatt from Innsbruck, and it's such a pleasure to see you all live again. It's my pleasure to introduce the next speaker of the session, Klaus Mølmer, and he is going to talk about interactions with quantized laser pulses. Please, Klaus.
Thank you very much, Rainer. Let's see, yeah, the mic came on. I would first like to thank the organizers, like the previous speakers, for organizing this conference, not only once, but twice. I can promise you that I have looked at least twice as much forward to this conference as I usually do to the ICAP conferences. So it was worth the effort already. As Rainer just said, I'm going to talk about interactions of pulses of light, quantum light, with matter. It's actually a question that has concerned me the last 30 years. I entered quantum optics not as a student, but after having done my undergraduate studies. And then, of course, I had to accept what was in the books and what my mentors were teaching me. But you always have some nagging questions. Why don't they describe this problem and take these things into account? Or why don't they actually ask questions about this particular property of the system, but always use a certain description that you could maybe question would be always sufficient? And that is what I want to tell you about here, that maybe the interaction between light and matter that we all love so much and we use so much has to be re-examined if you want to get at least correct calculations. So this is also a very timely issue. It was not always a question of big concern, but in modern times we are talking about stationary and flying qubits. We're talking about quantum technologies. We actually want to transfer quantum states, maybe from a point A to B on a European map here, or you want to do gate operations where you are employing sometimes photons as the quantum bits, and sometimes you use the atomic systems as the quantum bits. So you're really storing quantum states and you are manipulating quantum states, and I want to address how we describe that in the most proper way when you're dealing with traveling light. And that is actually why we advocate the use of light so much, is that it can travel, for example, along fibers, as you see here. So here is one of the candidate proposals. This is from Gerhard Rempe's group at the MPQ, where a single atom in a cavity can be interfaced with a traveling single photon wave packet. And in this way you can entangle the atomic system and the single photon wave packet, and it can travel on to other cavities that you see in the background, and in this way you have a communication of quantum information between these systems. Now the inner functioning of this proposal by Rempe, and these are experimental studies by Rempe, is that the atom has two hyperfine split ground states, and if you are in one ground state, then you will be resonant on the optical transition with the cavity mode. And this actually means that if the atom populates that state, that resonant interaction will split the cavity mode, and an incident photon will not be resonant with the cavity. It will be reflected on the input mirror and go out again. While if the atom is in the other ground state, then it's as if there's no atom in the cavity. The photon will enter and leave again, and it will therefore have a different phase on this return of the photon. So that's an interface between a single atom qubit state, if you take the two lower states as the qubits of the atom, and then the phase of this photon wave packet, which is also carrying a qubit type information. So that is really brilliant. Here's a proposal from the quantum dot community, where you're also reflecting light off a quantum dot system, which is just depicted here, and the light is traveling on to the next quantum dot, causing an entanglement operation between the two. It's indicated that there's a photon wave packet traveling here between the two systems. And also in the microwave community with superconducting qubits, it's proposed to interface different superconducting qubit units by microwave wave packets who can travel between these different devices here, so as shown by this little wave packet here. And what is shown in the upper plot is actually a diagram suggesting that even a single chip will use waveguide systems on the surface of this chip to waveguide microwave excitations from component to component. So all very, very exciting, and you have probably all seen these many proposals. Just one last proposal, which is very interesting, is to use acoustic waves. So the superconducting devices can also be hosted on silicon wafers or materials where their contraction due to a piezo-type electric effect will actually lead to acoustic waves that can propagate and can be a mediator of quantum interactions. These phonons will play exactly the same role, will play exactly the same role as photons do. And when I'm talking about photons in this presentation, you could also think about phonons in acoustic waves. Now, coming to the issue, there's a small print in quantum optics textbook about what we are really learning when we learn to quantize the radiation field. So you probably all saw this idea that we have Fock states, number states of photons. You can make superpositions of these Fock states, superpositioned here with coefficient Cn. You can also sometimes draw phase space plots because every mode of the quantized field is like a harmonic oscillator. So you have like x position and momentum quadratures, and here's a Heisenberg uncertainty relation depicted for a coherent state, and this is for a squeeze state. I just mind you that all these pictures and this kind of superposition state is all for just one single mode. And the typical textbook example is a standing wave mode in a cavity. So you have a standing wave, the Maxwell solution has been found, and then you're now asking how many photons are populating that particular Maxwell wave. If you have something that travels, it will typically be a beam or maybe a pulse. And if you have a traveling beam like that, it's not confined in the same way as a standing wave is in a cavity. So here I may have a detector, and that detector counting photons is not going to count what is the total number of photons in the beam. It's going to count as function of time. It's going to measure the flux. If you count for longer, you're going to count more photons. If you count for shorter, you're not going to count all the photons. So this n sitting in the superposition up here is playing a kind of different role in the traveling beam. I would like to think of the traveling beam as something you could cut in slices, and in every little slice of that beam, you could say that's a quantum field, and there could be a number of photons in that slice being 0, 1, 2, 3, 4, the same in the next slide, the next slice, the next slice, and the total quantum state of the light is actually a very complicated object here. Light is like a stack of pancakes, where in every one of these pancakes, I turned it around 90 degrees, you have a certain quantum state. And of course, it's not a product state of what is in the first and the second and third slice, it will actually be an entangled state. Coherent states of light are the easiest one. They actually correspond to a coherent state component in each slice. But if you have a total of, say, 5 photons in a few microsecond long pulse, it actually corresponds to 5 photons that are distributed over a kilometer of beam. And of course, quantum mechanically, that can be a very complicated or certainly very entangled object. So this is a story of 2 superposition principles that I just want to present in this brief presentation, namely the one that has to do with the Maxwell theory, the one who says that we have wave packets that are propagating and we have interference phenomena, and then the quantum superposition principle, who says that if you have photon number states, for example, you can form superpositions of such photon number states. These are not conflicting, but they're 2 different things we are talking about. We are talking about the wave theory of light, and we are talking about the quantum theory of the photon number that is in those waves. And of course, this is again only describing a single, for example, a standing wave. You can take many, many modes of the field, and then you would write maybe a superposition state like this one, where you specify the number of photons in each of these modes with a common C big N coefficient that is going to tell you what is the state of the light field. And it's really the combination of those 2 aspects that I want to talk about when you interact with moving light. So the small print again, let's just take a simple system here where I have a simple light source, a 2-level system. I'm exciting it over and over again, and it emits resonance fluorescence. So there's going to be a beam of light. That beam of light is going to have a kind of steady state intensity. It's going to have a steady state spectrum. But of course, when you do the counting measurement, you will have clicks on your detector, so there will be fluctuations present in this beam. And how do we describe the quantum state of such a beam? It's actually super complicated. In the Schrödinger picture, it's literally impossible, because the expansion on number states is just so super entangled. I mean, wait for a second, you have 1 million photons extending from here to the moon, and that big quantum state, that's really a quantum field, and it's a complicated state, and you don't write out that wave function. So what do? Well, we look for what is the observable we're interested in, and then we look for that instead. And in fact, the program in quantum optics has been to completely eliminate the light field and just look at the emitter. Because if I can calculate the evolution of the emitter, then I can relate the properties of the field to the emitter. The mean intensity of the beam is going to be given by the mean excitation of the atom. The mean field in the beam is going to be given by the mean dipole of the atom. And similarly for correlation functions and spectra, they'll be given by the temporal dynamics of the emitter. And that's the quantum optics textbook version of this. So we write down a master equation, and very often it's called the source master equation because this is the source of the field, but we're actually only looking at the equation for the source, not for the field itself. So the atom has a Hamiltonian, and then it has damping terms, and if you are familiar with master equations, you know this form, and if not, don't care too much, but there's an operator expression for how your density matrix evolves. These L are quantum jump type operators. It's the atom jumping from the excited to the ground state under emission of a photon. And of course, everything I'm talking about here could be replaced by more complicated emitters where we would still have an expression for what is it that emits the light, what is the atomic or internal process that emits the photon. So what we do in quantum optics is actually to solve that equation. And then from that equation, we can calculate mean properties of the beam, like intensity and also fluctuations in the beam. And then, of course, part of that is that the mean field or the field itself is solving Maxwell equations where you have the source terms, the charges and the currents, and these terms sitting in the Maxwell equations relate exactly these atomic properties to how the field propagates through space. When I'm only talking about the observables like intensity and field, I'm in fact talking more like a Heisenberg picture. I'm talking about the field operators and their values. So it's an observable point of view, and this is exactly what we do in the quantum optics literature. So we can calculate mean values and correlation functions. All has been good for 60 years, but now we want to talk about the quantum state of the light because we want to send pulses, we want to absorb pulses, we want to interact with pulses, and we want to manipulate those pulses. So this is not done sufficiently in the Heisenberg picture anymore. So it doesn't mean that textbooks have not speculated about what's the quantum state of a light pulse. So of course I can take a light pulse like shown here, just take any shape who solves the Maxwell equation, propagating Gaussian pulse, for example. I can define the creation of a photon in exactly that shape. I can describe Fock states which are populating exactly that wave packet, and I can also make superposition states of these Fock states. So everything that holds for a standing wave in a cavity also holds for such a wave packet, and so as long as it just propagates through free space, the quantum state content is preserved. The 5 photons will also be 5 photons when it reaches Madrid, for example. And the coherent states will look like that. And there are funny and exotic states that people like to produce, and you'll hear about them in the next talk also, because they can store logical qubits effectively against losses, and they will also be useful in this transmission protocols, because these states are multi-photon states. The logical qubits 0 and 1 are 2 orthogonal states, and even if you lose a photon, you will still be able to recover the quantum bit here. But then how do we make these states, and how do we manipulate with these states? How do we interact with those states? So that's really my concern here in this talk. So how does a quantum pulse interact with, for example, a stationary qubit? So I'm showing you here the pulse. It approaches the 2-level atom. It's going to interact with it. And then we ask ourselves, what is that interaction actually looking like? What's the Hamiltonian for that interaction? And what is going to precisely happen? Is it the same as if you take an atom and you fly it through the spatial profile of a standing wave field, where you also have a time-dependent coupling because the interaction is on and off as you actually experience the field? Because that problem has been solved in the literature. There's a time-dependent coupling in the Hamiltonian, and the Hamiltonian is a Jaynes-Cummings interaction where you can absorb or emit photons while the atom is increasing or decreasing its energy. And the answer to that question is, of course, no, otherwise I would not give this talk. And there are several reasons it's no. So in fact, it's a little bit redundant, but I'll just give you a few reasons for that no. There is an exchange of quanta, as described by the Jaynes-Cummings interaction, also in this case. Right? You can absorb the photons, you can also emit photons. But in the cavity, there's only one mode you're interacting with. And that's because the cavity discretizes the frequency spectrum, and other modes are far away in frequency. So you are not going to transform a photon from one frequency solution to another frequency solution in the cavity. While in the freely propagating case, there's a continuum of frequency modes present. It doesn't take any perturbation to change the shape of the light pulse. And in fact, you know that because if I send light through a piece of glass, I can delay a pulse. If I send it past an atom or a cavity, I can turn it into a dispersive light shape. So there's exactly this issue that the pulse can change its shape itself. And that's the Maxwell part of the superposition principle, which is now getting entangled with the photon number part of the superposition principle. Because if you talk to a 2-level atom, that's a nonlinear process. One photon does not interact the same way with a 2-level atom as 2 photons do, as 3 photons do, 5 photons do. And therefore, your one photon state or your one photon component will maybe come out in a different mode function than the 2 photon and 3 photon and 4 photon states. You get multi-mode output when you interact with such an atom. And that means it's all these ideas of just saying we add a photon to the field, we subtract a photon to the field, is actually not correctly calculated, because these interactions do allow, or actually it's hard to avoid that you start exploring this big continuum of frequency modes. So here I like the photon wave packet with a snowball in hell. It's super easy to completely disturb and modify such a wave packet shape. So I just confront here again the two pictures. The real physical system is you enter in with a wave packet, you interact with the atom, but on the right-hand side there's a spectrum, continuum spectrum available for the propagation of the light, while on the right you're talking to a discrete mode and you have a simple Hamiltonian description. So how do we describe it? And we have a trick here. So the trick says that such a wave packet could have been released from a cavity far away. And that cavity, if it has a suitable output coupling strength, then this mode function will be exactly released. That output coupling strength is given mathematically here, but don't bother so much about what it looks like. You can imagine that you have to turn up this G and turn it down again in a certain manner to produce a certain wave packet coming out of your cavity. So I'm actually synthesizing a wave packet. So it's a theory trick. I'm not asking experimentalists to do this. I'm just saying that as a theorist, you can think about a wave packet as something that comes out of a cavity. So the system now consists of this cavity and the system I'm scattering on, which is a 2-level atom, and then I have the light from those two systems combined, which is drifting off into infinity after this interaction. So the interaction is going to be described by Hamiltonian and damping terms. So the Hamiltonian is the good old James-Cummings interaction, but the strength is not the U function, it's actually this G function, because that's the strength by which the field is leaking out of the cavity onto the atom. Okay? So that's one part of the story. Second part is there's going to be a damping, and damping is describing the photons which are running away. And if I see a photon out here to the right, I really don't know if it came from the atom or it came from that cavity. So it's an interference term between the cavity emission and the atomic emission. So this is a classical argument. You could also compare this to what's called input-output theory in quantum optics, which has exactly the same form, or the Ewald extinction theorem from the 19th century in classical electrodynamics, saying that the field coming out is the field coming in plus whatever the scatterers are emitting along the way. So this is my Hamiltonian, this is my Lindblad term in my master equation, and there's nothing more to my talk than you have to solve this equation, okay? Because that will describe the interaction between the pulse and the atom, okay? And so now I just wrote it formally the same way as we always write the master equation. But there's a funny little miracle happening that I have to tell you, and I have the time to tell you. There are terms here which are very natural. Here I remove a photon and I excite the atom. That's very natural. This cavity a kilometer away can lose a photon who leads to excitation of the atom. But this other term, which is due to the Hamiltonian being emission, has to be there, but it's actually the atom getting down to the ground state, creating a photon back in the cavity again. That sounds like nonsense to me. The cavity is a kilometer away. It's just made to produce the photons that are streaming towards the atom. But there's a miracle happening, because in my master equation, there is this L dagger L terms. And if I take these L dagger L terms, you can see I get A dagger sigma terms also from here. And they cancel from the Hamiltonian. So the eventual real equation you have to solve will have no terms where photons are running backwards in this system. So this is a chiral Hamiltonian, if you like, or at least excitations only move to the right in this particular system. And eventually the cavity will be in the vacuum state, the pulse has passed, and we have now solved the atomic dynamics in the presence of a pulse which is traveling by. So it's a simple equation. It's not any harder, of course, than any other master equation, and any QTIP or any program you might like to use can just be told what is the system, what are these operators, and then it solves this equation. So I'm actually pretty happy with this being a simple theory. But I'm not done yet, because I would also like to know what is the state of the light after the interaction with the atom. Because some of these schemes are actually made to moderate or manipulate the state of light. And I've just completely absorbed the light and let it run away as decay here to the right. But what is the state of that light field? And I already told you that that state is completely impossible to describe. It may be super complicated, populating many, many modes, a whole continuum of frequency modes with superpositions of Fock states. So very complicated. the applications we have in mind in quantum information science are very dedicated. We want to have one mode coming out with one photon less or one photon more or a certain manipulation happening to it. So the second best question we can ask ourselves is, what is the state content of a particularly interesting pulse mode here? Maybe the one who contains the most of the light, or the ones where we aim to actually have a photon subtracted or added or whatever this process does. So instead of asking what's the quantum state of the multimode field, I just choose at random, not completely random, but I choose any mode shape that I want and ask what is the quantum state of that particular mode after the interaction. That's a single mode question. Now can I also turn it into a theory that I can actually solve? And of course, if I can do the trick once, I can also do it twice. So I can put up this little fiducial cavity with an incoupling strength GV of t so that it will exactly absorb this V of t mode function. And that actually means that solving this problem consisting of two oscillators and my scatterer will tell me what is the quantum state of light in that particular V mode given any arbitrary quantum state that I put in the incoming U wave packet. So this is what I think is the solution to the question I addressed in the beginning. How does a quantum pulse interact with a quantum scatterer? So let's move on here. So formally, you have this U cavity and the V cavity, as I call them, but two harmonic oscillators, and then the system you're scattering on. Solve that master equation, and you have found what happened to your pulse of light. And I intentionally actually draw it as one that looks different from this one, because very often such atoms will cause a dispersion effect on the shape of the pulse. So example number one, stimulated emission. Beautiful example. You have an atom who is excited. You come in with a pulse with one photon in it. Will you get stimulated emission and two photons out in the same mode? And there's a competition, as you can see, because stimulated emission likes you to come out in the same mode. Natural spontaneous decay would actually like to come out with an exponential tail. These are not the same, and this is exactly reflecting the multimode character of this problem. But if you, for example, take this shape and you make it look like an exponential, which has in it also the stimulated emission effect, you can actually get a fairly high probability that you come out with two photons in the mode. So we have calculated that because, I mean, you have to calculate it to check if it's true. So what I'm showing you here is the population of different quantum states. I just alert you to the green curve, which is the probability as function of time of having two photons in the V mode, the outgoing wave packet mode. And you can see that probability actually goes almost up to 1, which means that you have almost unit probability of having two photons coming out in one and the same mode. Not exactly 1, 96%. Okay, and that's the maximum we could get. So you cannot get the stimulated emission into single mode with higher than 96% fidelity. An example from the MPQ group is to scatter coherent states on the single atom in the red cavity that I told you about in the beginning. There's a phase shift if you are in one qubit state that is not there if you are in the other one. So if you scatter a whole coherent state, you will actually get a superposition of the coherent state and minus the same coherent state. That's a beautiful story. Is it true? Well, that requires that the wave packet being scattered is also the same for the two, and is the same for every single Fock state component. So if you want to test this, you have to do a calculation where you solve this by the master equation, where you actually see how much are we going to explore the multimode character of that continuum of field modes. And the good news is that it works, of course, very well, but not exact. So if you come in and the atom has no decay itself, you have almost unit probability for the cat state, and you get these beautiful Wigner function plots. If you add some atomic decay, it will naturally also dephase the system, and then you get not so nice Wigner function, but I think it's still good enough to call this a kitten type state. But this is not so much to flag the result, but just to say that here's a method now we can actually calculate this. Nakamura in Tokyo has a similar experiment where he makes a cat state in a cavity by nonlinear interactions and a Kerr effect. Then he releases the cat. And the question is, of course, when you release that cat, does it stay single mode? You're releasing it while the nonlinear interaction is on. It could go terribly multimode. When we calculate it, it's not so bad. We actually get a pretty good single mode Schrödinger cat state. So I don't want to be known as the guy who kills proposals that exist in the literature, but I like to validate proposals in the literature. So, and finally, a surprising result, scattering a single photon on an atom just changes the mode, but it will be a single mode coming out. If you scatter two, it will very often come out multimode. Okay, one photon scatters, the other one is almost not seeing the atom at all. So this is complicated. And we tried to look at a superposition of 1 and 2 photons. Can I split those into orthogonal components to do a quantum gates on photonic qubits? And the fact is that the 1 photon does come out in one mode, but the 2 photons typically come out multimode. It's very complicated, and here's the distribution of populations on these different modes occupied by the 2 photons components. So this is a very complicated output. It's not very nice and coherent. But then my fantastic postdoc, Fan Yang, he said, let's put 2 emitters, one after the other. And we were lucky, I have to admit that, but putting just 2 atoms after each other, we actually have only a single mode output from this system. So the picture we have in mind is that the single photon changes its shape on the first atom, it changes it once again on the second atom, but the 2 photon state really goes into multimode, but then after that it returns to just a single mode. And that mode is orthogonal to the 1 photon component and can therefore be manipulated for quantum computing. So very, very exciting phenomenon. Okay, we're approaching red light. I will reach my conclusion on this slide. Sometimes photons move, and that is what we like about them, right? So, I mean, we're not going to get away with that problem, but we have to then describe what is going on when we interact with them. And moving light is fundamentally multimode. It's fundamentally the stack of pancakes I was talking about. And if you just assume it's single mode and do a calculation, you're just ignoring the dissipation into these other modes or the loss of population into these other modes. So what I presented here was a way to calculate that and maybe also to optimize that. So the quantum information protocols that rely on such a precise handling of the stationary and flying qubits by these interfaces, they really need a treatment like this one. And the good news is it's actually not harder than the simplified theory we may have used until now. It's just different, right? You have added this extra damping terms, and then you have to have this funny engineering of how the pulses are made with the G functions, but otherwise it just works. If we can restrict to few incident and outgoing modes, traveling modes, which are all solutions of the classical wave equation, then we can analyze this system with this new master equation. And I call it new because of the appearance of the master equation, but it has the usual form of Hamiltonian and damping terms. And the theory, of course, applies to any bosonic wave. It's exact if we can assume a Markov approximation, I mean the use of damping terms and linear dispersion. So for acoustic wave propagation may also be described by this theory. And with this, thank you for your attention.
Thank you, Klaus, for this nice presentation. I'm sure there are questions. Sure, Bill.
I would have been disappointed, Bill, if you would not have a question.
Yeah. Okay, so I want to go to your calculation about the stimulated emission and the fact that you only got 96%, or you were able to get as much as 96%, however you want to look at it. Now, what I'm wondering is, what kinds of things did you vary, and what approximately were the results that were best? So the kinds of things I can imagine is, what's the beam waste at the atom? Yeah. What's the shape of the pulse? What's the width of the pulse? These are the kinds of things that I can imagine going into this. So what did you find?
So first of all, here everything was just 1D transmission. So I considered only a single transversal mode in all of this. So there is only the longitudinal mode function to vary. And in this calculation, we were varying exactly that. Okay, so we can play with optimal control theory to actually just take any shape and just iteratively make them better. In this case, we found that just an exponential fall off where we vary that parameter was enough to reach this maximum. And also, just to add to that, if I go to 4 photons in, 5 out, it gets much better. Because then the stimulated emission, of course, wins more and more. Yeah. And you don't have to care so much about this remaining spontaneous part.
So that's the main thing that makes this not work, is the remaining spontaneous part.
Yes. The fact that the atom is actually always decaying. It's sitting there on the waveguide, and whatever excitation you put into your system, the fact that it couples to the incoming pulse means that it at the same time also couples by decay.
Yeah.
And it is a trick that you can sometimes balance those exactly so you get perfect absorption.
Okay, what I'm not understanding, though, is you've sort of suppressed the control of the transverse modes. Yeah. But obviously that's going to have an important effect, because it's going to tell you what's the Rabi frequency of a single photon, which is obviously going to be important if it isn't big compared to the decay rate. Yeah. So there must be something in your assumption about what's happening with the transverse mode.
Yeah, there's a lot, and in fact, I mean, I gave this talk in Paris, and Jean Dalibard asked me the same question. So whenever you talk to people who don't send their light through fibers, but through space, then this question pops up. And the answer is, of course, that the scattering on the atom will lead to scattering into different angles. And this will be like decay channels into other directions than the one you're actually looking in the forward direction. This can be handled by the theory, but it's not part of my example. So this is true. The incoming pulse, I can describe any 3D wave packet that is approaching my atom, but if I really want to know the content of any mode going out, I have to consider that there's loss into other directions.
Sure.
Yeah, that's true. But we know how to do it, but I will write that paper now because
Okay.
good people ask that question over and over again. Yeah.
There's a question over there. You make it really hard to repeat the question.
Yeah. So let me repeat the question. And you can just ask again if I don't repeat it enough. So when I show these standing wave cavities, of course, then you can also do ring cavities where you have the traveling wave. You have only unidirectional motion of the light. And does that make a difference to what I was presenting here? It certainly looks more like a wave packet could be flying through such a cavity. That's absolutely true. I think that the crucial question is actually the size of the cavity. What is the difference between the eigenfrequencies? Because also the ring cavities, of course, they have their resonances, and these resonances are also discrete. And if they are far away from each other in frequency space compared to the interaction strength, you will now be talking to a mode of the traveling wave, a traveling mode in the same cavity. But that will also be well described as a single mode, and it will still be different from the pulse which is propagating in a continuum where you have all frequencies available. So I think that's the main question. Of course, we also can replace this little two-level system by a real cavity with a system inside, because that's also a quantum system. And then we can explore the regime between long cavities with small free spectral range and short cavities with large frequency spacing between the eigenmodes. And we see a lot of the interesting physics having to do with multi-mode intra-cavity interactions. So if that was related to your question, then this is certainly an interesting issue, and it's not trivial at all. It has to be discretized or solved that way.
There's one more question over there.
Yes. So in the second to last slide, where you had these two photons dispersing over one or two atoms in succession, I was wondering if there's any sort of restrictions or maybe conditions on these two atoms, like the spacing between them or any of that has been imposed, or just there are two atoms, there's two free particles. Yeah.
This is thank you for the question. This is a fortunate case because the light is only propagating in one direction, and we are wave guided, so there's no divergence of the beams. Then the distance actually doesn't matter in this particular case. If there was propagation in both directions, then there would be standing wave interferences. But because there's only free propagation in one direction, it doesn't matter here. Our assumption was that the atoms would be identical. Later on, we actually tried to vary. What if they had slightly different detuning, slightly different coupling strength? And it was very robust because it's almost like an optimum to have identical atoms. So this was made together with Peter Lodal. You see him there, and he's one of the quantum dot people. So he's very critical to inhomogeneities, and we found that this is relatively robust to that.
Thank you.
Are there any other questions? There's one right here.
No, so thank you for
please
giving me
repeat
the
the question?
opportunity to clarify that question. So the question is it really sorting because the two photons just come back to the same mode again? And it's actually true that this mode function in which the two come out look very much like the one where they come in. It's actually even closer to the time-reversed version, but of course a Gaussian looks the same when it's time-reversed. So it's true, the two photons leave in the same mode. My point is that mode is orthogonal to the mode where one photon would leave. So the one photon is going out in a different mode than the two photon component. That means we can split them off by some frequency generation, and we can do a phase shift on one component, recombine them, and then we have done a gate in a photon sense. So you are right, it's the same mode, but it's the different one for the one and the two photon components.
There's a question from the online Q&A. Philip Treutlein asks, how can the detection of the pulse after interaction be integrated into this formalism?
Thank you very much. That's lovely. So we have actually just put an article on the archive. On another good day, I could have given a talk about stochastic wave functions and measurement back action. So there's no problem for us in taking the master equation. Actually, if you know the master equation for your unobserved system, you also know how to fix that in the case where the system is observed. So I can put a photon counter out here, and that would actually make these L operators act as discrete quantum jumps from time to time. You could also put homodyne detection out here, where you beat with a local oscillator, and then you get a more complicated stochastic differential equation. But it's actually perfectly fine to take this as your starting point, and then include spontaneous effects out measurements, the random outcomes of measurements, the same way as we do when we simulate measurements of fluorescence in general. Well, I'm looking at you, Joseph, but I should look into the computer screen or a camera somewhere. Sorry about that.
I think thank you all for your questions. I think we're at the end of this talk. Let's just give a handful to Klaus. Thanks for your talk. And we are going to continue with the second speaker of the session.